When you look up at the night sky, you're not just seeing stars. You're looking at a history book, an epic 13 billion year story of cosmic construction, ancient collisions, and stellar creation. But how in the world do you even begin to read a story that's written in starlight? Well, that's exactly what we're going to figure out.
You see, stars aren't just balls of hot gas. They're more like cosmic fossils. They perfectly preserve the chemical conditions of the gas clouds they were born from, billions and billions of years ago. So if we can learn to read a star's chemistry, we can unlock its age, its origin, and its own unique chapter in the grand story of our galaxy.
All right, so here's our game plan. First, we'll figure out how to pull a chemical fingerprint from a single star. Then, we're going to trace where those chemicals even came from. We'll investigate the universe's element factories. After that, we'll see how astronomers are gathering millions of these fingerprints in a massive star survey. And finally, we'll get to the really good part, the huge galactic mystery this evidence has uncovered. Okay, first things first, we need to know what we're looking for. The real key to a star's past isn't just what it's made of, but the exact ratio of the elements inside it. This is its unique chemical fingerprint. Now, before we go any further, we have to get a really quirky bit of astronomy jargon out of the way. When an astronomer says metals, they don't mean just iron or gold. To them, a metal is anything on the periodic table that isn't hydrogen or helium. Yeah, you heard that right. So for our purposes, even the oxygen you're breathing right now, that's a metal. It's a weird but totally crucial idea for this whole investigation. So the lead detective in this whole operation is a number called Fe/H. It is the single most important part of a star's chemical profile. It just compares the amount of iron in a star to the amount of iron in our own sun, which we use as our cosmic measuring stick. So why iron? Well, it's because iron creates a bunch of really strong, clear signals in a star's light, which makes it pretty easy to measure accurately. Now, this scale is logarithmic, and that's what makes it so powerful. A star with an FeH of 0, it has the same iron content as the sun. Simple. But a star with a value of -1 doesn't just have a little less iron, it has only a tenth of the amount. And -2? That's just 1/100th. This lets us compare stars across this huge range, from ones way richer than our sun to the truly ancient stars born when the universe was barely seasoned with any metals at all. So how do we get these numbers from a tiny speck of light trillions of miles away? Spectroscopy. It's amazing. We take the star's light, spread it out into a rainbow, and then look for tiny dark gaps in that rainbow. These are called absorption lines. Each element, like iron or oxygen, creates its own unique barcode of dark lines. And the strength of those lines tells us exactly how much of each element is in that star's atmosphere. Okay, so we've got the fingerprint. Now for the really cool part. We're going to trace where those elements came from in the first place. This is where we go from forensics to history, and we uncover the story of the cosmic factories that built the very stuff of the universe. Right after the Big Bang, the universe was, well, pretty boring. It was almost nothing but hydrogen and helium. Every other metal, the carbon in your body, the oxygen in the air, the iron in your blood, all of it was forged in the nuclear furnaces inside stars. It's this incredible process called nucleosynthesis. Stars live, they create new, heavier elements, and when they die, they explode, blasting all that enriched material back out into space to seed the next generation of stars. And it turns out there are two main types of these element factories, and here's the crucial part. They work on totally different schedules. You have type 2 supernovae, which are the explosive deaths of really massive stars. They happen fast, within about 10 million years, and they're great at pumping out what we call alpha elements, like oxygen and magnesium. Then you have type Ia supernovae. These are exploding white dwarfs, and this whole process is much slower. It takes over 100 million years to get going, and this is the universe's main factory for iron. And that, right there, that is the absolute key to our entire investigation. You have alpha elements made quickly and iron made slowly. So the ratio of alpha elements to iron, something like the oxygen to iron ratio, it acts as a cosmic clock.
If a star has a high ratio, it means it formed from gas that was only enriched by those fast type II supernovae. But if the ratio is low, it means enough time had passed for the slower type Ia supernovae to start polluting the galaxy with iron. This gives us this incredible direct link between chemistry and time. So when we find a bunch of stars that are low in metals overall, but really high in those alpha elements, we know we're looking at an ancient group, some of the first stellar generations born in the Milky Way. And when we see stars with a lower alpha to iron ratio, we know they're younger. We can literally piece together a galactic timeline just using these chemical clocks. So we have the theory, we have the forensic tools, we have the cosmic clock. Now we just need evidence, and to solve a mystery the size of the entire Milky Way galaxy, we're going to need a lot of it. Let's look at how astronomers are gathering this evidence on a truly massive scale. This is where incredible projects like the GALA survey come into play. GALA stands for Galactic Archaeology with Hermes, and its mission is, well, exactly what it sounds like: to dig through the stellar fossil record and piece together the history of the Milky Way. Think of it like the biggest galactic detective agency ever assembled. And just to give you a sense of the sheer scale of this investigation, GALA's most recent data release contains detailed chemical fingerprints for nearly 1 million stars. I mean, just let that sink in. Almost 1 million cosmic fossils, each one with its own story to tell. This is big data on a cosmic scale. And this is what the raw evidence file actually looks like. Each row here is a star. You've got its temperature, its overall metallicity, there's our old friend F over H, and then these crucial abundance ratios, like magnesium to iron. These tell us its history. You can see right away how that second star, with its low F over H and its high M over F over H, is almost certainly way older than the other two. We are literally reading history right off this table of numbers. So, our detectives have gathered nearly 1 million clues. They've used them to crack some of the galaxy's biggest cases. But when they tried to put together the complete story of the Milky Way, they ran head first into a totally unexpected plot twist. First, let's talk about the wins, because this method has been incredibly successful. Astronomers have used it to chemically pull apart the Milky Way's young, thin disk from its older, thicker disk. They found entire streams of immigrant stars, leftovers from smaller galaxies that our Milky Way ate billions of years ago. They can even do something called chemical tagging to find long-lost sibling stars that were born from the same cloud but are now scattered all across the galaxy. It's amazing stuff. The methods clearly work, but here's the problem. When astronomers built a simple model of how the galaxy should have evolved, a straightforward story where stars form, enrich the gas around them, and the galaxy slowly builds up its metals, the model didn't match what we actually see. There was a huge, glaring discrepancy. And this brings us to one of the biggest unsolved cases in galactic archaeology, the G-dwarf problem. You see, that simple model predicts that we should see tons of very old, very metal-porous stars in our cosmic neighborhood. But we don't. We find way, way fewer than the model says we should. It's essentially a case of missing persons, or missing stars. Where did all the old metal-poor stars go? This mystery basically proves that our simple story is missing a major piece of the puzzle. There are a few leading theories. Maybe our whole idea of the galaxy as a closed box is wrong. Perhaps there's been a constant rain of pristine, metal-poor gas falling into the galaxy from the outside, diluting the chemical evidence over time. Or maybe the very first massive stars pre-enriched the galaxy more than we thought. The case is still wide open, and trying to solve these deep mysteries hidden in datasets with nearly 1 million stars, that requires brand new tools. More and more astronomers are turning to artificial intelligence to sift through this absolute mountain of data, to find the subtle patterns we might miss, and to help turn all these raw numbers into a rich, explanatory story about our galaxy's life. And that brings us right back to where we started. Every single star is a fossil, a message from the past. We've learned to read their chemical language, and it's revealed these incredible tales of galactic mergers and cosmic creation. But as the G-dwarf problem proves, there are still major mysteries left to solve.
And you have to wonder, what other incredible cosmic stories are hidden up there in the starlight, just waiting for a detective to come along and read them?